Hi there. So we're talking about leftist heaps, and this is not a political thing, so let's not go there. It is a heap, but how it's constructed is a little different than what you and I are used to, only because we want to be able to merge multiple heaps into one new one. In the heaps that you and I have gone over so far, there really wouldn't be an easy way to merge a heap of two heaps together, just two regular heaps. So there's this leftist heap in order to enable us that ability. So it uses a binary tree. Notice it's not a search tree, it's a binary tree. It merges heaps much easier and faster, and that's the algorithm that I'll go over here in a little bit, so bear with me here. Okay. It's also going to use established links that we already have, so if we're worried about pointers, how they work out, moving pointers and all that stuff, here's the good news. There's actually not a lot, so that's the good news too. The values still obey the heap order. Remember that highest number, if it's a max heap, is at the top, and then it trickles down to the bottom. Uses null path to maintain the overall structure, which I'll cover a little bit later, so bear with me on that one. And then at every node, the shortest path to a non-full node is along the right-hand path, or rightmost path. And again, that's something that I'm going to go over here in a little bit, so bear with me on that. But this part is the amazing part. And again, think of massive, massive heaps, not the small ones that we do in class, but massive, massive heaps. To find them in, which makes sense, would be at the minimum heap, would be at the top, easy O of 1, deleting. All these are very, very fast, even if we have a massive heap. So this algorithm really could be helpful if we have multiple large data sets that we've put into a heap for some type of ordering, same overall concept of why we do heaps. This one is, again, an algorithm to help us merge multiple heaps together. So what does a leftist heap look like? Well, here we got one right here for you. So notice a couple of things. Number one, it's still, this one's a minimum leftist heap because the minimum is at the very top. Notice that every parent is less than its child. Pick any node that you want. This one here, that one's less than its parent, or sorry, is greater than its parent. Its kid is greater. So again, the further we go down, the actual greater the value in this minimum heap. And we've seen that before. There's nothing crazy about that either. The other interesting part about it is here's why it's called leftist. And again, I'll get into the algorithm, the construction here in a little bit. But notice it's a little heavy on the left-hand side. You'll notice it. This one has a left child and a right child. This one has a whole bunch of left kids. This one has a whole bunch of left kids. There's some that have right, but it's very heavily pushed on the left-hand side. And again, bear with me on that because I'll go over the algorithm here in a moment. So notice there are some similarities to what you've had in heaps before, but there's some differences too. The other one I'll get to, and that's the numbers here in a moment, that's really, really important. Bear with me for a sec.